Example 7.6, we're going to study a car driving around a circular path, and the force that is acting as the centripetal force in this case is static friction between the tires and the road. So consider a car that's driving in a circle of radius r at a speed v. What is the minimum coefficient of static friction between the tires and the road that's required to keep the car on that circular path so that it doesn't skid? Now, remembering back to Newton's first law, if there were no external forces on this car, it would just continue in a straight line at constant velocity. In order for it to turn, there must be some external force acting on it. That external force in this case is the friction force. So the friction force is acting as the centripetal force. The friction force points toward the center of the circular path. That changes the direction of the velocity vector and causes the centripetal acceleration. So this is our top view of the car driving around a circular path. When I draw a free body diagram, I'm going to look at a different perspective. Okay, my free body diagram is oriented from behind the car as though you were standing on the ground behind the car watching it. So from behind the car, its velocity is going into the board. Up is the positive y direction, and to the left is toward the center of the circular path. That's the radial direction, toward the center of the circle. So that means we can draw the forces involved. Gravity and the normal force are both in the y direction. Gravity points down as always. Normal force points up. And the centripetal force provided by friction points toward the center of the circular path. So there's the static friction force that points toward the center of the circle. Now this is a Newton's second law problem, so I'm going to do my usual Newton's second law analysis. Because we have friction involved, I'm going to look at the y direction to get the normal force. Sum of the forces in the y direction is 0. The car is not accelerating up and down. So we've got n minus w equals 0, or n equals mg, which often happens. Now we have a value for the normal force, and we'll look at Newton's second law in the radial direction. So this is the new form of Newton's second law that we've learned about for dealing with this direction of the motion. Our centripetal force is static friction, and according to our sign conventions, because it's pointing toward the center, we give it a minus sign, and our acceleration is also pointing toward the center, so that gets a minus sign as well. Centripetal acceleration equals v squared over r. We learned that a few lessons ago. So both these minus signs cancel, and the friction force is mu times n, or mu mg. Those m's cancel, and we get this relationship. Now this is saying that this is the value of the coefficient of friction that's required to keep the car stuck on the circle so that it doesn't skid out. Your textbook gives you some numbers, and when you plug in the values, it gives you this. That's just for the particular combination of V and R that the problem gives you. But what's interesting about this number is that typically for rubber tires on a concrete road, the coefficient of static friction can be as high as about 1. So this is significantly less than that, which means that we're safe to drive at this speed and on this radius without skidding. Now you can see from this expression that the faster you go, the more friction is required to keep you in the circle. The smaller the radius of the circle, the more friction is required. So you probably know this from experience and common sense. If you try to go too fast around a circle, your car begins to skid. Or if you do too sharp a turn with a small radius, your car might begin to skid. That's because the amount of friction that's required is related to the speed that you're going around the turn and the radius of the turn. Also, if you could make gravity stronger, you can't adjust this on Earth, but if you were on a planet with higher gravity, you could take your turns faster too, because G would be a bigger number. Okay, so that's example 7.6. We'll do some more examples in the next few videos.